Hello, everyone. You are in Islander FG, and welcome to API-Induced SSRF, How Apple Pay Scattered Vulnerabilities Across the Web by Joshua Maddux. If you'll give me just a moment, I have some announcements that you should visit the Black Hat Arsenal, which is in the business hall inside of Oceanside and the Shoreline ballrooms in this hotel. If you would please silence your phones, I would appreciate that as well. And also lunch is in Bayside AB from 1 to 2:30. And with that, give us a round of applause for Joshua Maddux, please.
All right, so I'm going to lay something on the table right now. This talk is about software architecture, and I'm not apologizing for it. Now, you may be wondering, how in the world did this guy get in here? Software talks are boring. And I would kind of agree with you. I used to be a software engineer and sort of still am. Architecture talks are especially boring. But most of those are on the positive side. You build something, it scales, it makes money, and so now you're an expert. But I'm going to look at the negative side. Where does software architecture go horribly wrong? Obviously, when it scatters vulnerabilities across the web. So, first, a bit about me. I'm Joshua Maddux. I have a math degree, but I've been a web developer for a while. Then I got started with bug bounties, and that shifted me towards security. Now at PKC, I've been doing a lot of security work for clients. We're located in Huntington Beach, about a 4-hour drive from here. You can visit us at pkc.io. All right, so now for an overview of the talk. First, I'll go over a couple of terms combined to form my criticism of Apple Pay. Then I'll do some demos. The focus is on finding a large number of easy-to-exploit bugs, so the demos will be quick and pre-recorded. These demos are all against my own redeployments of open source stuff that has already been fixed. I won't be attacking any live e-commerce systems, since most of my disclosures to those are still private. Lastly, I'll have some general principles for designing better APIs. Like you may have picked up, I'm going to go pretty hard on an architectural decision made by Apple here. In discussing the security of software architecture, people tend to bring up vague principles and notions of who's responsible for what. But I'm going to back myself up with concrete examples. Better yet, these examples should be educational, if you want to start testing SSRF yourself. So, on to definitions. So there's this existing concept of a class break. It's the idea that software tends to be vulnerable in multiple places at once. Past research is focused on cases where you might have a single weak piece of code, say SQL injection in a CMS plugin, or Heartbleed. It gets built and deployed to a lot of places, and when it's discovered, there's a huge rush to get your instance patched. You could frame a lot of the talks at this conference as class breaks. And currently, there's a lot of tooling to help companies stay on top of this. But there's another level that I've seen a lot of this year. It's not new, but it is becoming more common. A company will create an API or spec at this top level that isn't itself vulnerable, but in some way induces several people to write vulnerable code. Some familiar examples may be the JWT none algorithm, or the problems that have popped up in recent SAML implementations. So if you're looking for sheer volume of vulnerabilities, thinking at this top level can be a lucrative place to start. I couldn't find an existing general term for this upper level, so I'm going to call it an inductive weakness. And here's the definition. It's a design flaw that encourages multiple parties to write vulnerable code with a similar exploit pattern across differing software stacks. For example, we may say an API induces SSRF vulnerabilities, or that an API has an inductive SSRF weakness. This is wordy and might not seem entirely justified right now, but should make sense once we get to the demos. And now for a refresher of the other term, SSRF. It's been around for a while and stands for server-side request forgery. A lot of people confuse this term with CSRF, client-side request forgery. In practice, very different bugs. Naming similarity is kind of unfortunate. SSRF is a bit of a hot topic right now because it's a lot easier to exploit than it used to be. We'll see why towards the end of this section. So, start off with, say this attacker on the top left wants to interact with an internal facing server on the bottom right. But the attacker doesn't have direct access. They can only go through the public facing server displayed in the middle. The attacker then tries to find some weakness in that public facing server. In the past, people have taken the URL and put it somewhere like a host header or the body of some XML in order to get the server to hit the desired location. There are a lot of different ways that you can go about trying to get that URL and try to get the server to hit it. But the goal is to relay a request through the server in the middle as if it were a proxy. Typically, we only call it SSRF if the attacker can use the proxy-like behavior to access or harm something internal. If you can get stuff back, it's easier to exploit and called transparent SSRF. Otherwise, it's called blind SSRF. The exploitability is tied to how permissive the target server is and how much sensitive stuff is available internally there at the bottom right. So, what can you do with this pattern? Turns out it's quite powerful right now because of the defaults in popular cloud environments. This has been the most fruitful approach for me so far. Google Cloud and AWS both expose credentials by default on 169.254.169.254. Depending on the permissions assigned to the instance, this token can often access private storage buckets or other stuff. It's basically allows you to, if you can hit this and get the token, you can act as if you are that instance. There's even been some pretty credible speculation that the AWS equivalent of this endpoint was the first step that enabled the recent Capital One breach. But I never go that far. I just stop here and report it. The other thing to note is that on screen you see a curl command. That in itself doesn't demonstrate a vulnerability because I'm already inside the box in this case. It's when you can externally tell the server to hit a URL and give you back the token that it, or something else sensitive or cause some harm that it becomes SSRF. Also, to keep the naming straight, this slide is also not an inductive weakness. AWS and GCP aren't causing people to write weak code. They're just widening the consequences if people do. But what this slide does demonstrate is that if you want to do SSRF on someone using AWS or GCP right now, you have a very easy payload to start with. So, what are some other easy things to try with SSRF? People have already criticized AWS and Google Cloud a lot for providing the UE center you saw on the previous slide. There have even been some rumors that AWS is in the process of improving things in response to the Capital One breach. So I won't dwell on that criticism too much. File URLs are another interesting thing to try, especially on older stacks. The other interesting thing is that if you can proxy through GET requests, you can do reflected XSS. You just have to point to a URL with some malicious HTML and JavaScript, though then it's technically not SSRF because the attack scenario is different. It is a fun thing to keep in mind though, because if you're trying to get true SSRF and you're just like not getting through on anything, but it's on a GET request, you still have this other option if you want to then, try to submit for a bug bounty or something. But aside from these, the general first step is just to try a bunch of ports and different payloads and see if you could try something like CouchDB or memcached running internally. There's even, I believe, I didn't link to it in the slides, but there are a bunch of SSRF cheat sheets out there that you can run through. But what if you want to dig deeper? There's been a lot of past work on cross-protocol attacks via SSRF. Gopher URLs are interesting because you can inject a wide range of characters that will eventually go into the TCP stream. So you have a lot of room for interacting with other protocols like TCP or SMTP. There are a lot of different ways to get there though. Sometimes it might be necessary to set up a server that redirects to the protocol you want. Other times you might just go with an HTTP URL and exploit a bug in the URL parser. Probably the coolest work on this is the Orange SciTalk, a new era of SSRF. However, libraries are getting stricter and a lot of the easy stuff has been fixed. This is a really fun area of research though, and I expect there will be additional changes discovered in the future. But for now, in case there were any gaps in my explanations, does anyone have any questions on SSRF? There are microphones. Okay. So now we'll get on to the meat of the talk. We'll combine our two terms to describe the Apple Pay web. Before diving in, it's important to note that Apple Pay is composed of 3 different technologies under one brand. You may be familiar with the Buy with Apple Pay button, which appears on both in-app and Apple Pay web. There's also the upcoming Apple Pay card, but I have no idea whether it fits into all of this. But I'm only criticizing Apple Pay web since it has some problematic requirements for merchants. So, say you have an online store. Within nomenclature, we would call you a merchant. What does your website need to do to support Apple Pay web? When the user clicks the Buy with Apple Pay button, Safari spits out a validation URL, which is on one of about 30 apple.com subdomains. Then, in your client-side JavaScript, you have to send the validation URL to your backend. You might be able to see where this is going. Then, your server needs to grab a merchant session from that validation URL and return it to the client. This is all a bit wordy though, and it's much better as a diagram. Luckily, I already have one. So this should look familiar. Following the typical flow, as a merchant, your server in the middle would take in that URL to know which Apple server to connect to grab a merchant session. But depending on your infrastructure, if you implement in the way Apple originally documented, or deployed their example code by default, this is a really dangerous functionality to add. The endpoint isn't ideal for an attacker who wants to do SSRF, since the validation URL is user supplied. They're basically doing their load balancing in the user's browser. I've asked Apple for some justification of this requirement, and after several months, I have no idea why it is still there. In the original WWDC talk, there's a vague explanation of handling the case where a merchant is compromised, but that doesn't explain why they allow the client side to choose between validation URLs instead of having just one. And ultimately, they're providing a whole new way for attackers to compromise merchants instead of protecting them. Google Pay certainly doesn't do this. Some merchants were safe for one reason or another, but we'll get to mitigations later. Right now, it's time for a demo. All right. So, these demos are not particularly deep attack chains, but besides demonstrating breadth of attack surface, they should be illuminating if you're interested in testing SSRF yourself. Just please, if you try this at home, only try it against sites where you have permission, and report what you find. Don't go snooping against private storage buckets. So, this first demo is against the Google Chrome Labs project that was deployed publicly via App Engine, but not in a production environment. I don't point this out to shame Google or the developer. Instead, I want to demonstrate that even talented, qualified people on modern software stacks were affected by the Apple Pay design flaw. So, here's my own redeployment of this project so we can see what I did against Google's deployment. As you can see, it has a buy with Apple Pay. Oh, oops. So. Okay, so as you can see, it has a buy with Apple Pay button. So it's getting an error because my deployment isn't fully configured. But our attack will still work. So if we go to the network tab, this is a fairly basic way of attacking this, but if we go to the network tab, click it again, we can see a request going out to this endpoint called validate. It's pretty small there, but it's in red. It's getting an error, but we can still use it to attack this site. So normally you might attack this with something like burp or MITM proxy, but I'm going to go old school with curl. First, we clean up some headers. Then we modify the validation URL just so we can conveniently replay different values. So first I'll try something basic. I'll just try to hit example.com to see if we can proxy through the endpoint I'm hitting. It'll take a couple tries here. So just proxying out to example.com like this isn't SSRF, but it is a useful first step in testing this stuff. And now for the actual SSRF. Let's try to hit the instance metadata server. And remember, this is deployed as is, very similarly to how it was. So it looks like we're getting through on a Google Cloud box. And then by feeding in metadata.google.internal, we can confirm that that's the case. So from here, it's just a matter of browsing directories and seeing what works. For whatever reason, /v1 beta1 is less strict about headers than /v1. I have no idea why that is. But we can keep browsing. And now we're in the directory at the GUI center. We can see what permissions this box has access to. And even retrieve a working token. For whatever reason, I put a black box on part of it, but it is expired by now, and that instance is offline. So for the next demo, we'll be attacking my own deployment of a page that was on webkit.org. The issue was fixed, but I deployed the vulnerable version from a few months ago on wk.jmaddux.com for the purposes of this demo. Don't worry though, my deployment is offline by now. Importantly, just like the previous demo, the code on webkit.org was written by a well-qualified developer at a large tech company. This may even be more convincing because it demonstrates that even developers at Apple were not immune. In the original POC I sent to Apple, I just grabbed an AWS token. I have this deployed on Google Cloud though, so it'll be a chance to try something a little bit different instead of just instance metadata. All right, so here you can see my own deployment of the page that was on the code that used to be on webkit.org. I love this art, but this button here looks promising too. So it turns out we can also see a merchant validation request happening here once we open up the network tab. It's different code from the previous example. You can see merchant validation.php instead of the node endpoint from the other one. But the attack will be similar because of the requirements imposed by Apple for this Apple Pay endpoint. So we'll proceed much like we did with the previous one. All right. OK. So we can try to hit instance metadata, but we're not going to have any luck because the request methods aren't lining up in our favor. And this is something you'll probably encounter if you test SSRF for yourself. But we can see that we do get proxying out to example.com. So this is still a promising endpoint to try. So at this point, it's just a matter of trying different payloads. And it turns out that because of this is just a classic, an old school PHP app, just a classic file URL will work. So this is a pretty deeply seated architectural problem. And I reported it to Apple back in February. But what has Apple done to mitigate this? So far, just documentation changes. Importantly, the documentation used to pretty much walk you through the process of adding a vulnerability to your website. Now the documentation has this little warning box. They seem really optimistic about how many developers actually read those. However, if you do happen across these warning boxes and read them carefully, the instructions are now valid. But for the existing clients, I can't imagine too many developers are constantly visiting the documentation to check what warnings were added. So, and here's the disclosure timeline. There's not much here. The main thing is that I reported this back in February and haven't seen any meaningful architectural changes. In my original proposal, I asked for Apple to deprecate the current API and phase in a new version that didn't have these problems. But they haven't engaged with me in any discussion on that. They've just updated documentation and removed their bad example code. A couple of weeks ago, I even gave them a heads up to say, hey, I'm speaking at Black Hat and DEF CON. Can you give merchants a heads up? But again, ghosted. So we'll get back to this later. But for now, how would you mitigate this? My favorite mitigation so far has been to just remove Apple Pay support entirely. This probably won't work for everyone, though. But for everyone else, it's important to manually parse the validation URL and check the host against Apple's list. It's kind of ugly to copy and paste 30 domains into some config file, but that's pretty much what you have to do. A couple of payment providers have do this out of the box, though. So far, I'm just aware of Stripe and Braintree, so if you're using one of those two, you're safe. That's been a fairly big hurdle in trying to claim bounties on this stuff, is that a lot of sites use Stripe and Braintree, and then it's Stripe and Braintree handling the validation. But it really depends on the payment processor. Some payment processors leave this up to individual e-commerce sites to decide how to do. But what if you want to defend more broadly against SSRF? From my experience, very few people are protecting egress traffic, but when they do, it provides a pretty big speed bump. That may make more or less sense depending on the size of your organization and just how your network is laid out. Netflix has also done some great work in proactively defending against the GUI Center in AWS. There's, I believe, a blog post. They talked at Black Hat recently, and there's a lot of good things to look into there. But in general, though, it's just good to take a look at what ports are open locally on your servers and add passwords even when the network layer is theoretically protecting them. But on the other hand, here's some stuff I've seen that has some holes in it. Regexes are tricky, and I wouldn't recommend them as a mitigation for this issue. But besides the point in this slide, I would also discourage against relying on a check to start at apple.com, because then if there's an open redirect anywhere on any apple.com subdomain, an attacker can use the open redirect to circumvent your check. Narrowing the check to specifically allow the 30 Apple Pay related subdomains is better. There's no way of getting around it, really. If you have to support Apple Pay Web, you really should go to Apple's updated documentation and read through the warnings they've added. The architecture is still bad, but at least the documentation doesn't walk you through the process of adding a vulnerability to your website. So that wraps up the specifics on Apple Pay Web and our first inductive weakness. I'll have more to say on Apple towards the end of this talk, but in the next section, I'll move on to another pattern that can induce vulnerabilities. But for now, does anyone have any questions? Nope. OK. So move on to webhooks. So a lot of people are creating webhooks right now. Webhooks they're becoming a fairly common and useful way to tie the web together. There are a lot of them out there right now, and nobody seems to agree on how they should be implemented. So what's a webhook? Here's an example from Twilio. It's a way of telling us your service to, a service to call your URL as soon as an event happens. Here, you can see I have jmaddux.com/SMS registered, so Twilio will send me an HTTPS request every time it has a new SMS message. So, how have people been exploiting webhooks so far? They've gone after the sender of the webhook. In this case, Twilio. It's pretty similar to how I would test Apple Pay. Instead of entering your own server as the URL, you put the AWS instance metadata IP or try to do some cross-protocol stuff. This is just a general challenge of implementing webhooks. And it's not an inductive weakness because there's no central party inducing this pattern. Webhooks are just really useful for a lot of businesses. Luckily, lots of people have already exploited webhooks in this way, and you can find a lot of bug bounty write-ups where people did exactly this. I haven't done much of this, though. I've done something a little bit different. What have I been doing? I applied the same inductive weakness model that worked with Apple Pay. Instead of going after the sender, I look for an attack surface the sender might be inducing in the listeners. And it turns out for Twilio, this approach works, and it works well. How do the receivers of the webhooks know that the message is coming from Twilio? Twilio provides an HMAC, similarly to how most webhooks are done. They call it a signature, and that probably will make the cryptographers in the room cringe, but conceptually it does kind of help to think of it as a signature. Assuming that the receivers actually check it, it's not too bad. But when I took a look, most related open source projects failed to look at the HMAC. So I had these unauthenticated endpoints lying around. Once I started poking around, it became apparent why. Twilio's examples didn't check the HMAC either. And setting aside the bad example code, this seems to indicate an architectural problem. I argue that since the easiest way to receive an HMAC authenticated webhook is to disregard the HMAC, that is a design flaw. And the specific kind would obviously be inductive weakness. And now for a demo. So this demo is slightly different in that the example code was not on a public-facing server, so I didn't get any credentials from Twilio themselves, or any bounties. But it is still worth showing because it was copied and pasted elsewhere. So here's where I started, just looking at the repo for Twilio example code. On the README, there's now a warning to protect your webhooks, but it turns out the example code still doesn't do that. Even further, yeah, we can see go down there and check that there's no authentication. But going even further, it takes in this media URL parameter, and that looks promising, knowing what we know. The example webhook is even quite generous because it fetches the contents of that URL and puts them in a public-facing directory. So you might be able to guess where this is going. All right, so in this next tab, I'll have the code deployed as is on a Google Cloud instance. It tells us to send a text message, but we don't need to do that. This webhook is unauthenticated, so we use the snippet I have on the right and pretend we're Twilio, sending over a CSV attachment. But because of the URL we sent, the server dumps an access token into that public directory. And by the way, this access token also expired long ago. So here's the disclosure timeline, fairly similar to the Apple Pay one. But you might be wondering, are Twilio's competitors doing any better or worse? Because in general, when you try to say, oh, this has a design flaw here, it's good to look at what else is out there. But turns out with Nexmo, it's much worse. Not only is the architecture similar, but you have to contact support to even get them to send you an HMAC. And even if you do contact support, some of their webhooks don't have that option. I don't have much to say about this. It's pretty much beyond hope. So let's move on to another webhook. So GitLab does something similar to Twilio, but with a static token instead of an HMAC. So the implementation is a bit different, but the same level of optimism is there. I don't have the static token pasted here because it's just simply a value that you configure with GitLab and they send to you. But here I have the body of the event that they send over. And here's just the body of it if you enable it. So you might be able to imagine what I did. I simply found a server that was receiving this webhook. As usual, they were not validating that it was coming from GitLab. I won't name names, but it's a webhook. I can't imagine that what I found was the only unauthenticated one. And in this case, I'm trying to make the case for that this is actually a design flaw in the way GitLab is sending webhooks, or in just the general architecture that webhooks are being sent by a lot of parties right now. But in any case, I decided to tweak the sample push event and send it over. Right off the bat, I was able to modify the repository URL and trigger extra builds for arbitrary repos. I didn't have any success deploying arbitrary code, but I did find one nasty consequence. It turned out I could store XSS payloads. The script would execute whenever someone clicked a particular button on their build population page. And you don't need to log into anything to do this attack. So this really epitomizes the point that I want to make. So far, we've been asking what vulnerabilities are in the software, but an equally important question is what vulnerabilities does the software create? Once you start asking this question, you can find lots of stuff. And this is, yeah. All right, so these next few slides are going to be a bit text heavy, but I am making an aggressive claim here that nearly everyone's doing webhooks wrong, so it's necessary to lay out some alternatives. This is probably the coolest but the least practical one. You can encrypt your webhooks, your outgoing webhooks with an authenticated cipher. The upside is that in the act of trying to use the information you send them, people will inevitably be authenticating it. But the downside is there aren't a lot of good libraries for authenticating this, especially once you look at what's available across different programming languages. So this isn't very practical right now, but we can always dream. So going a little more practical, you can do what Plaid and Square do. If you limit your webhook payload to an event ID and expect the receiver to fetch it, you're really not inducing much attack surface. The downside is that this does require an extra request from the listener to you. You do also have to worry about path traversal if that ID is within a URL segment, since a lot of people will forget to encode data they inject into URLs. But it is probably a good middle ground, especially if your API just doesn't have a whole lot of attack surface in general. Yeah. But the least aggressive approach, and this is probably the most practical, and it works well for existing webhooks, is just to be more proactive about making sure people use the HMAC. Most webhooks already do one testing request to ensure the URL being registered is publicly reachable. So it's not a huge change to do 2 requests instead. It's then a matter of policy to decide what you do if the URL appears unauthenticated. Even if you just warn your customer, that's still miles ahead of what other webhooks are currently doing. I'd really like to see webhooks start doing this, since it's low risk and backwards compatible in a lot of cases. All right, so a lot of this so far has been negative, and intentionally so. But there is an upside. By designing an API to be defensive from the ground up, you have a lot of ability to prevent vulnerable code from being written. So let's look at one API that didn't and one that did. So Salesforce and DynamoDB are very different products. But there is an interesting area where they overlap. They both have had to act as a source of truth, with some complicated business requirements piled on to the point that each had to implement a custom SQL-like dialect. But they went about that in very different ways. If you've ever pen tested a web app that uses Salesforce somewhere on the back end, hopefully this has been on your radar. I've definitely gotten a lot of mileage out of it. Sometimes user input propagates out to a place where you can inject into this API call, much like you would do a SQL. So how has Salesforce tried to mitigate this? More documentation. This is becoming a theme. At first, this might seem to be inevitable, given what Salesforce is required to do. But when Amazon tackled this, they did something interesting. DynamoDB forces you to parameterize your precondition expressions. If you try to concatenate a raw type in there, it's treated as invalid syntax. You have to put it into the expression attribute values object. There are other ways you can go about attacking these calls, but they're a lot more limited than if you could inject into the syntax itself. This call is kind of cumbersome, but I think it's a worthy trade-off, given the strength of protection this provides. All right. So now we'll get back to Apple, since they're probably the worst offender in this talk. After 2 months of silence, they came back with this as justification for their architecture. Developers are responsible for implementing whatever security and networking best practices makes the most sense for this environment. And when you see this, you think, oh, that is a perfectly reasonable statement. And this is all true. But the implication is that Apple has no culpability in this. And that the responsibility should all be shifted onto developers. But luckily, I've got another great quote. If you've built a chaos factory, you can't dodge responsibility for the chaos. And you might be able to see the name there. But both of these statements are right. Developers should not introduce vulnerabilities, but When you expect people to add an endpoint somewhere, you have some level of responsibility for the attack surface you create. But that's a purely ethical argument and might not appeal to a lot of people. So let's look at some of the financial aspects of inductive weaknesses. Once researchers start hunting for this stuff, I imagine there will be a large financial incentive for API designers to start thinking about it. I got some nice bounties out of the Apple Pay issue, and none of my work needed very difficult payloads. And also, none of those bounties were from Apple. So I think it's fair to assume that once this talk is over, some people are going to start applying my approach. Also, think of where new bounty hunters are going to report stuff. You're seeing the most embarrassing consequence here, but what if my talk hadn't been accepted at any conferences? There was a lot of private embarrassment as well. Apple didn't seem to think that SSRF was much of an issue, but most websites I reported to did. I wouldn't be surprised if they held that against Apple. All right. For another angle, in software development, there's this concept of technical debt. It's the idea that cutting corners early on has costs that accumulate as a project grows. With regular tech debt, the fixes reside in your own code base. So the interest rate is tied to the growth of your own code base. Both inductive weaknesses, the fixes are in your client's code, and it's deployed all sorts of different places. So the interest rate is tied to how much adoption your API sees. At a certain point, if you want to pay down the debt, you can't just push out an update to your own code. You have to contact your customers, probably push out a breaking change to your own API, and then tell your customers they have an API, that they have a vulnerability because they chose you. But here's really what I'm asking for, and it should be pretty cheap if you think about this stuff early. I'd really like people to start scrutinizing their example code because it gets deployed a lot more often than you'd think. I mentioned in response to the Apple Pay issue, one of the steps Apple took was just simply remove example code from their website. But I did see that example code deployed in various forms across different places. But in the process of scrutinizing your example code, you may even discover inductive weaknesses. If Apple had done so, I wouldn't have had much to talk about. Also, keep in mind that a lot of developers don't realize quite how dangerous it is to hit an externally provided URL. But if there's one thing I want people to take away from this talk, it's that documentation is no excuse for bad architecture. And here are the long-form takeaways. You can find a lot of vulnerabilities by looking at an API, finding a flaw, and seeing who integrates with it. We need to place more scrutiny on security weaknesses that induce others to write vulnerable code. And while there's been a lot of recent work on SSRF, the software world has a long way to go in defensively coding around URLs. All right, here are the acknowledgements. I'd like to thank Jonathan at PKC for asking some of the initial questions here, Arte at PKC for pointing me to the Nexmo stuff, Ken at PKC for helping with the presentation, and Andrew at the EFF for legal assistance. All right, and thank you. Does anyone have any questions?